Okay, so in this video, in section 4.4, we're going to start talking about the natural logarithm function. And we're going to revisit the properties of natural logs and converting logarithms to exponentials and exponentials back and forth, back to logarithms. And we're going to be using the natural log often because you're going to start to see why the number e and the natural log function are so useful. They just make so much math so much simpler. So first, hopefully you remember the natural log function looks like this: y equals natural log of x. Anytime you see natural log ln of x, that's the same thing as saying y equals log base e of x. So all a natural log is a log with a base of e. If you want to convert log base e, sorry, this g is bothering me. If you want to convert log base e to exponential form, you could rewrite this as e to the y equals x. You always take the base of the log, and that becomes the base of your exponent. And then the two other terms switch sides of the equal sign. So this is really what we're going to be talking about mostly in this section. So hopefully you remember the graph of the natural log function looks like this. Remember, the natural log function is just the inverse of the exponential function e to the x. E to the x and natural log x are inverses of each other. So they're reflections of each other over the line y equals x. Their x and y values are all flipped. And if we talk about the properties of the natural log function, remember, when you take the log to any base, of 1, it always gives you 0. So obviously the natural log of 1 is going to give you 0. That's a common rule that you want to remember because that can simplify a lot of problems you're working on too. Anytime you take the log of 1, no matter what the base is, you always get 0. Another rule that can really help you out is if you have an exponent such as 3 to the log base 3 of 72. Whenever the base of the exponent, if an exponent is being raised to a logarithm, the base of the exponent and the base of the log in the power are the same, your answer is the other number, is the exponent, or is the number that inside the log. So 3 to the log base 3 of 72 is 72. 15 to the log base 15 of 2 is equal to 2. So with that being said, e to the natural log of x is the same thing as saying e to the log base e of x. So that has to be x. So anytime you see e to the natural log of x, simple. The answer is just x. And then another rule from Algebra 2 that we're going to be using here is a rule that looks like this. Basically, if you have a log base 3 of 3 squared, whenever the base of the log and the number you're taking the log of match, your answer is going to be the exponent. So log base 5 of 5 to the 10th is 10. So with that being said, if we have natural log of e to the x, that's the same thing as writing log base e of e to the x, so that has to be x. So anytime you see the natural log of e to the x, you should know that that is equal to x. Okay, so this brings us to the properties of natural log, and you can pause and read through all of these, but this is all stuff you should have had in Algebra 2. So here we're going to start simplifying exponential expressions with natural logs and with e in them. So what we're going to have to do is use our rules of exponents that we have been working with, especially from 4.1, to simplify some of these problems. So hopefully, if we're going to simplify e to the natural log 3 minus 2 natural log x, remember, if you have a base of an exponent and inside the exponent 2 terms that are subtracted, that's the same thing as saying e to the x minus y is the same thing as saying e to the x over e to the y. So if we split this up and write this as e to the natural log 3 divided by e to the 2 natural log x. Now, if we simplify here, we've got e to the log base e of 3, which is 3. Now let's simplify the denominator. We've got e to the 2 log base e of x. So we could rewrite this as, remember, when you have two numbers in an exponent that are multiplied together, you can write it as a power to a power. So we could rewrite this as e to the log base e of x squared. Do you see how I did that? Because these two are multiplied together, I'm going to write them as a power to a power. So now I know inside the parentheses, e to the log base e of x is x, and then that is squared. So this expression simplified can be written as 3 divided by x squared. Okay, so this brings us to a problem that looks like this. If we have e to the x squared times e to the 2 minus 3x equals 4, again, if we use our properties of exponents, we have two terms with the same base multiplied together, so we can add their exponents. So first, we want to see that this is a power to a power. We can rewrite this as e to the 2x times e to the 2 minus 3x equals 4. So if we combine these two, we can add their exponents. So we've got e to the 2x plus 2 minus 3x equals 4. So now if we combine like terms, we get 2x minus 3x. We've got e to the negative x plus 2 equals 4. So now, to get x out of the exponent, what we're going to have to do is we're going to have to take the log of both sides. Hopefully you remember this from last year. If we take the log, if we're going to take the log of both sides, since this is in terms of e, we want to take the natural log. Because remember, the natural log of e is 1, right? Because the natural log of e is log base e of e, which is 1. So if we take the natural log of the left side, we have to take the natural log of the right side. So in taking the natural log of this side, now we can move the exponent down. So we're going to have negative x plus 2 natural log e is equal to natural log 4. Natural log e is 1, so that just goes to 1. So now we have negative x plus 2 equals natural log 4. And to solve for x, we subtract the 2, so negative x equals natural log 4 minus 2. So x is going to be equal to negative natural log 4 plus 2. And you can plug that into your calculator or you cannot, but that is the exact answer to our solution to this equation. Okay, so if we have an exponential or a logarithmic equation that looks like this, if we want to solve for x here, first thing we need to do is get the natural log by itself. So we need to divide both sides by 5. So we get the natural log of 2x equals 8 over 5. Now, to get this 2x out of the natural log, the only way you can do that is to convert to exponential. So if we rewrite this as log base e of 2x equals 8 over 5, if we convert this to exponential, remember the base of the log is the base of your exponent, and then this becomes your exponent, and that's what it's set equal to. Now we've gotten rid of the logarithm, and now we divide both sides by 2. So we get x equals e to the 8 over 5 divided by 2. Again, that's the exact solution. Okay, so hopefully you also recognize common logs are just logarithms with a base of 10. Natural logs are logarithms with a base of e. So natural log of x equals y. Okay, so this brings us to the last problem, where if you're given a graph and you're asked to find the coordinates of the maximum and minimum points, what we need to do, obviously, is find the derivative of the function, and we need to set the derivative equal to 0, and that will give us the maximum and minimum values. So what we need to do is differentiate this function, and I rewrote it down here because it overlapped right there. So to find f prime of x, first we're going to have to break this up into u and v. So let's say u equals x minus 1 squared, v equals e to the x, u prime is going to be 2x minus 1, v prime is going to be e to the x. So we're going to say the derivative of negative 1 is 0. So now we're going to have vu prime, which is e to the x, times 2x minus 1, plus u v prime. So that's going to be e to the x minus 1 squared. So now looking at this, do you see if we can factor out an e to the x, and we can also factor out an x minus 1, just to simplify? So we're going to rewrite this as e to the x minus 1. Then left over in this term, do you see we've got a 2? Left over in this term, we've got an x minus 1. So now if we simplify further, we get e to the x minus 1, parentheses 1 plus x. So now we need to set this derivative equal to 0. So we're going to use a 0 product rule and say 0 equals e to the x, 0 equals x minus 1, 0 equals 1 plus x. And if we solve for x each time, do you see there's nothing you can raise e to here to get 0, to output 0. So there's no solution here. Here we get x equals 1, and here we get x equals negative 1. So x equals 1 is going to be this minimum point. X equals negative 1 is going to be that maximum point. So to find the coordinates, we just basically plug those values in. When x equals 1, we plug those values back into the original function. So f of 1 is going to be negative 1 plus 0 squared times e to the 0. So negative 1. So 1 point is going to be 1, negative 1, which makes sense here. And now we're going to find x equals negative 1. So we're going to have f of negative 1 is going to be negative 1 plus negative 1 minus 1 squared is going to be negative 2 squared e to the negative 1. So it's going to be negative 1 plus 4e to the negative 1. So that's going to be negative 1 plus 4 over e. So the second point is going to be negative 1, comma, negative 1 plus 4 over e. You can plug that in your calculator to get the decimal approximation. But that should put the y value somewhere around there. So that's how you find the coordinates of the maximum and minimum points. So I hope this helped refresh you with logs and natural logs. And good luck with the prep quiz.